Hello and welcome everyone back to my another video tutorial. Last time I recorded you a tutorial about reinforcement learning that is related to my new library that I call RockRL. And basically there I showed you how I implemented and how I trained a lunar lander to land a rocket in a space on the ground safely using the gym environment and how to train it and so on. It was pretty impressive and it took only 20 minutes to train that agent. So this time I decided to pick a little harder task and because before there was a discrete environment and it's pretty easy to implement a PPO agent to learn a discrete environment. And what is discrete? Well, discrete is when, for example, we have four outputs, for example, four engines, and we want to turn on only one of them. So either 1, 2, 3, or 4. And in discrete environments, usually we need to turn one of them. And that's it. That's the only thing that our engine needs to learn. But right now, as you might see, this kind of robot, walking robot or running robot, I don't know how to call it. I trained this on the continuous environment with the same library I used before, but this is way harder environment to learn because of course it's continuous. Oh, you saw it fold. And so basically this environment, we'll see how long it took for me to train, but basically it's way different because, for example, we have 2 legs, there might be 8 outputs, and for each leg we need to decide what angle we need to use. So this means we need to output a float number, and you can imagine that when we are playing around with a float number between 0 and 1 when deciding what angle to set our legs, there is I don't know, thousands or millions different possibilities for 8 legs, and to explore all of this takes enormous amount of time. And for this purpose, for this task, I implemented this continuous environment because it's more related to real world example what we would use in different tasks. So I'll walk step by step through my code, not getting too deep into it, but basically you'll see what this agent does, and I'll show you how you can easily train it by yourself. And in the next tutorial, I'll walk you through a hard environment. There is another environment that is with obstacles, and this is a challenging stuff. I really didn't saw a lot of code online on the Google that I could pick out of the box and train the agent to defeat this kind of hard environment. Of course, it also takes way more time than this simple environment. So let's look at the code. So basically, you remember last time I looked at this lunar lander and there was a lot of 4 different files with examples. Right now, I have only 2 files, one for test and one for training. So basically, let's go from the beginning. And right now, it's no purpose to train the agent on one environment because it will take a lot of time. So for this purpose, the same as before, I'm using a vectorized environment. You can check the code inside of this, what it does, but simply it creates our number of environments we want and puts them on different processes, and simultaneously we communicate with all these processes and we control of them. Oh, it's running. Well, okay, let's run. And what I do next, I need to use memory manager. As before, I used one memory for one environment, but because we will use multiple environments, I need to manage all of these memories. So next, I import the PPO agent from TensorFlow. And this time you'll see that instead of discrete environment, I'm using continuous, and we'll set it while creating PPO agent object. So, but you might ask, what's the difference between discrete environment model and kind of continuous? So I think I can open the lunar lander code and we'll see what we have there. If I will be able to move it to one side or another. And let's open this one. That's great. Okay, so you might see that here is my continuous model and there is my discrete agent. As you might see, it's in discrete model, it's pretty simple. We have our action space, for example, 4, and we use a softmax activation on this one, and we simply receive an output. But when we talk about continuous, we have a dense with action space and we use activation of 10H, and 10H fits our output from 0 to 1. And additionally, we need a sigma. Well, in discrete environment, we were able to calculate the sigma while getting the softmax output. And what is sigma, you might ask? Well, sigma is kind of special number that gives us exploration in our environment. This is kind of randomness. So for example, in discrete environment, if I'm having a probability of making one action of, for example, 60%, so in this case, this 40% uncertainty will be sigma, and we use this 40% to take a random action instead of this 60%. And when this kind of sigma decreases, our agent reduces the exploration and goes with exploitation to learn what it learns correctly. And this way it learns. But when we are talking about continuous environment, everything is a little bit different. We need additional parameter because there is, when we have a 10H output and we are not using softmax, we are not sure what action is good and what is bad, and simply it gives us float number. So in this case, we need to have additional parameter from our network. So this is called sigma, and it will have 1, and this is learnable parameter of this randomness. And we'll see what this value looks like in TensorFlow while we are training. And I add additional dense layer to this one to give additional learning stuff from a few dense, additional one dense layer with few neurons. So that's it, and I simply concatenate everything into one array and give it as output. And after that, when I'm doing prediction, I take everything as action up to the last index, and last index is sigma. You'll see about that. So we don't need this lunar lander code, I believe. I can close it, and if I open, well, critic model looks exactly the same. We don't need activation and so on. So what I do here while we are trading, we set the bipedal walker. I create 48 environments, but you can even increase this if you have a great GPU and you want to make everything faster. So I create the vectorized environment with a gmake, and I set it environment name, and it will make me this vectorized environment with my vectorized environment custom object. So next is crucial, the PPO agent. As you might see, I give it here actor model, critic model as we set up above there, and I set the Adam optimizer. Well, for this time I set the learning rate of 0.001, but it's pretty large learning rate, and it might not learn, or it might learn pretty fast. So for example, right now it learned me everything fast, but in practical, if I would like to get better model, I would set it even lower, but train it for longer. So this time it worked for me, but for example, if you would test and it might not train something for you, so try to decrease this learning rate. So then I set a different gamma, lambda, and C2 KL coefficient. Well, this is very important, but we'll talk about this in next tutorial. I'll show you everything about hardcore version. and I use grad clip, write command, train epochs annealing, and so on. Well, this is hyperparameters that are crucial in reinforced learning, and you should be familiar with that they are crucial if you are not first time facing, well, reinforced learning. So for interesting reasons, I print the summary and it should be here, right? Yep. And as you can see, here is my dance. So this is my, I believe this one is my action space, and this is my sigma, and simply I concatenate these 3 with 5, and I receive my full output. So I need to split later down. So what I do next here, I set the memory manager, mean average for saving best model and etc. And here you might see that I call reset environment. This gives us me states and dictionary. This is 10,000 episodes I'm interested to train, but usually harder the environment, more steps we need to train. And what we do is simply call action states, ag and act. So let's go into this, what's happening here. So before we cover this discrete environment, and right now we would like to see what happens here in continuous, and that's what I do here. I receive the probes from actor when I use the forward pass, and I need to split action probes and sigma from these probes. So simply I do it like this, and if it's not a test, I include this sigma as random stuff into the actions. Otherwise, I use my specific props as actions if it's simply a test environment. And that's it. I return these actions, props, and everything is fine here. Let's go back. And at each step, I call step on all environments at once, because it's way more efficient to use a prediction with a batch to the model, and it decides all, for example, 84 actions for all 84 environments, and it's way faster and way more efficient than doing prediction for every agent separately. So I save everything to memory and so on. Then I check which environment has finished. So this means which environment crashed or achieved the last maximum score of environment. And I simply reset this environment and call the train on this environment. And I do reset. And if the score was one of the best within the mean score, I save this agent and continue training while everything is printed into the terminal. And that's it. That's the whole logic of this training code. And you might see that's what is within the test environment. So let's cover it quickly also. Test code. So what I do here, as you might saw already, I ran the 4 different environments that are simply walking, and I do everything the same. The logic is the same as in the training code, but here instead of creating a new actor, I load already saved model. But sorry, I need to mention that I will not be uploading this model anywhere, because it's pretty easy to train it by yourself. And well, I want to save my space for better stuff on this. So I use the same memory manager as before. I'll run for 100 episodes and etc. And as you can see, I use the actor as predict states, and I receive probes and actions. Sigma separate the actions from sigma, and I believe sigma is not used anywhere, only actions, and I use these actions to the step and so on, so on, so on. And I save everything into memory, and again, as in the training, I check which environment finished their episode and etc. And I print the scores here. Of course, I could save it in some memory into the list to know what is my average score of these environments, but I don't need it. So also, you may see it's only 4 environments, but I could run, for example, 48 environments, and it would finish this me very quickly. Also, I could comment this render mode from human to not render me how this bipedal walker runs, but I only render this for you for interest to check this out, how it runs. I believe it's pretty interesting to see how it works. And that's it. I don't know what else to talk. It's pretty amazing. RockRL library. You simply write pip install RockRL like this. Install RockRL, and it will install everything what you need, and it will work. As you may see, I already have a newest version, but there is minor changes in these test codes that I will update, because I will add some kind of readme and etc files, and with that I want to fix all the bugs that you might face. So that's it. And yes, you might right, you want to see what is the training curves with this bipedal walker from Gymnasium. And yeah, let's see what are the requirements. If you're on Ubuntu, everything is way easier for you. You can use a higher TensorFlow, use the higher Gymnasium, and the specific RockRL that I use here. But if you are on Windows, you might need to use this specific version, because if you have GPU, otherwise it's up to you, but it might not work for you. And Gymnasium is also pretty hard to install, but yeah, we need to spend a lot of time on these things, and this one requirement is also needed. We need box.dd. That's great. So let's move on to the TensorBoard graph that I saved and I have here. So basically, there's no huge point to getting deep into the loss curves, because sometimes when training a reinforcement learning agent, it's pretty hard to know whether the loss is good or bad or etc. Well, mainly we need to focus on these kind of rewards, entropy, validation stuff, if it's improving or not. And for example, this is the rewards curve from this bipedal walker that I trained for 10,000 steps. And you might see that it trained for me around 10 to 40 minutes. I believe it was with 48 environments, and I achieved best scores at around step 2000 after 12 minutes of training. So this is pretty amazing, and it depends on your machine, what machine you have, and how fast you can train. But simply, you might see that it's pretty efficient, and you can leave it to train through the night, and in the morning check the results, and it will be finished, and everything looks great. And you remember I talked about sigma. We'll look at it. This is an additional parameter from our network. As you may see at the beginning, our neural network gave 50% randomness and exploration, and very quickly it started to drop, and after 1000 steps there was already left only 35% of this exploration, randomness, and etc. And our score started increasing, and somewhere here where it started getting pretty nice scores, it kept decreasing, and used only 10% as sigma for this kind of exploration. And later, when it wasn't able to get better results, as you may see, because there was no reward downsides and etc., I believe this model is the best, and this was saved one. It started to increase my sigma to a little explore. Maybe it could do better something, maybe there is better techniques to work on, etc. But it's really hard to say whether it was best model or not. But you might see that everything is correlates and it works. What I do have, I also have KL divergence graph curve. This is also pretty important curve, and what it shows us that KL divergence shows us the difference between previous actions and new actions after the training step. And usually we don't want them to explode too high, but yeah, you might see that there is no very high spikes. And in my code, I limit this kind of code not to allow these spikes. I use this KL coefficient. So this means that I add this kind of KL coefficient to my loss, and this way agent is not allowed to make too huge steps, for example, to learn not to walk. It's always incrementally learning something step by step, but with small steps. And this we can see these results in hard environments as bipedal walker hardcore, but I will show you this next time. And you might see that these curves looks pretty fine and amazing, and you might see that the rewards, it was pretty steady, and this was also very good, and my scores for these kind of agents are also very impressive. Yeah. So if I go here, you might see that where I'm running here, yeah, it's almost always gets more than 300. Well, here it crashed, I believe, but everything else is just fine. And if I open all of them, they keep running, and you might see that it's a little laggy for me, but only because I'm recording and my CPU is not the best one. So that's it about this tutorial. You can check the links below in description to find a link to my RockRL library, or also I'll put the link to this tutorial code where you can check everything else and try it by yourself. Sorry that I will not upload the train model, but next tutorial maybe with the hardcore version, when I show you demonstrated how it works, maybe I will upload this model because it's kind of challenging to train that model. And that's it about this tutorial. I hope this was really useful for you. You liked it, you evaluate what I do, and if you do, don't hesitate to smash the like button, subscribe to my channel. If you have any questions, what I should test, what I should try, whether what new I should implement or include into this library, you can leave a message in description or open the Git issue on GitHub where we could continue discussion, and I hope I will be able to help you. So that's it about this video and this kind of environment, and we'll see you in our next part. So thank you again for watching until the end, and we'll see you next time. Thank you and goodbye.